17.2 is about the equilibrium law. So in 7.2, we were introduced to the concept of the equilibrium constant, Kc, and discussed in qualitative terms what its value tells us about the composition of the equilibrium mixture. What we're going to look at now is the quantitative version, so we can actually see what the concentrations look like at equilibrium, initial, what is the overall change, so on and so forth, and using Kc in that equilibrium expression as well. In all the examples we're using, we're going to look at a homogeneous equilibria. That is where the reactants and the products are in the same phase. They're all gaseous or all solutions. They're not different because that would change the situation in which we're working with. We are going to be looking at 4 different types of calculations that we can use. The first one is calculating Kc when you're given the equilibrium constant. The first step you want to do is write down the balanced reaction because we need that stoichiometric reaction in order to get the coefficients for the products and reactants. Step 2, write the appropriate equilibrium expression. Step 3, substitute all the given values into the math problem and solve. Use an example. Hydrogen can be prepared by a combination of carbon monoxide and water at 500 degrees Celsius. At equilibrium, the concentrations of in the reaction mixture were found to be carbon monoxide is 0.15 molar, water 0.0145 molar, hydrogen 0.200 molar, and CO2 0.0200 molar. So again, step 1, write your reaction. So carbon monoxide is combined with water. To produce carbon dioxide and hydrogen. As it's written, it is already balanced. Next step is to write the equilibrium expression. So we have Kc equals products, so concentration of H2 times the concentration of CO2 over reactants, concentration of CO times the concentration of H2O. Step 3, substitute the given values into the appropriate concentrations. That being, H2 has 0.200, CO2 has 0.0200, divide that by carbon monoxide, which has 0.150, and the concentration of water is 0.0145. All these concentrations are the concentrations at equilibrium. Go through and do the math, and you get 1.84. As we talked about in 7.2, this tells us which side's going to be favored, and because this is greater than 1, barely, but it's greater than 1, that means the products are favored. But in this instance, it's very, very, very much in the middle and not so much as products solely. The second calculation is we will be calculating the value of Kc when given the initial concentration. So when we're given the initial concentration, we have to go through and find the final concentration. Step 1, just like before, write a balanced reaction. Step 2, under each of the reactants and products, write the values of the reaction. What we mean by that is you're going to need 3 lines. The first line is your concentration of your initial concentration. So you're going to be given the initial concentration of your reactants. You're going to put that number underneath the reactants. We are going to assume products concentration are 0 at the beginning of this reaction. The second line is the change in concentration. So change in concentration is the change in the amounts of reactants to reach equilibrium. We change reactants by subtracting them because we're losing them, and we change products, or we add that number into for products because we're adding products into this equilibrium state. What we need to keep in mind is that they occur at the same ratio as the coefficients are represented. The third line is the concentration of equilibrium. So this is the concentration present in the equilibrium mixture. How do we determine this? You take the concentration of the equilibrium equals the initial concentration plus or minus, depending if you're working with products or reactants, the change in concentration. And once we have those three things written up, you can write your expression, substitute in the values in which you're given, and then solve. So the example we're going to work with. A student placed 0.20 moles of PCl3 gas and 0.1 moles of Cl2 gas into a 1 decimeter cubed flask at 350 degrees. The reaction which produced PCl5 was allowed to come to equilibrium, at which time it was found that the flask contained 0.120 moles of PCl3. What is the value of Kc for this reaction? Step 1, write the reaction. So PCl3 gas is reacted with Cl2 gas. The product is PCl5 gas. Then we want to create our three initial change in equilibrium. So our initial concentration. We have 0.20 moles of PCl3 and 0.10 moles of Cl2 put into a 1 decimeter flask at 350 degrees. The reaction which produced the PCl5 was allowed to come to equilibrium. So remember, the initial concentration of PCl5 is going to be 0. Next, we want to look at what our change in concentration is, and ultimately we want to know what our equilibrium concentrations are. Finish reading the problem. At which time it was found that the flask contained 0.12 moles of PCl3. So that is the other piece of information that was given to us. We need to fill in the rest. We want to go through and figure out what the change is from the one we're given. So we go from 0.20 to 0.12. That gives us a negative 0.08 change, which means Cl2 also had a 0.08 change because it's a 1-to-1 ratio. And in turn, we have a positive 0.08 change because of our product, because that also has a 1-to-1 ratio. This means go through and do the math. 0.10 minus 0.08, we have a 0.02 concentration of Cl2 at equilibrium. And then we have 0.00 plus 0.08, so we get a 0.08 concentration of PCl5 at equilibrium. That being said, now we need to plug all this information into our equilibrium expression. So Kc equals our product, PCl5, over our reactants, PCl3, times Cl2. Substitute our values in. 0.08 over 0.12 times 0.02. That value gives us 33. Again, this number lies above 1, which means we're going to favor products. The third calculation which you could perform is calculating the concentration of equilibrium when you're given the Kc value. All right. We have two different types. We have simple and we have complex. Looking at simple first. If you know your Kc value and you know all your concentrations but one of them, you can substitute and solve. And so essentially you're solving for x. All right. The complex one takes a little bit more effort and time. So using the complex equation, we need to use algebra. So first, you need to know your Kc value, and you need to know your initial concentrations. 6, write the reaction if needed. Sometimes it will be given to you. Step 3, set up the table as we did before with initial, change in concentration, and equilibrium concentration. In order to solve for this, your initial concentration needs to be given. Your change in concentration is going to become x. So negative x for reactants and positive x for products. And then the number in front, you put a number in front of that x value if there's a stoichiometric or coefficient in the reaction. You're going to write the Kc expression and substitute in your values. Solve for x, and then find the concentration of equilibrium from every x. An example of this would be the concentration of CO gas plus 2H2 gives us CH3OH. So writing our equilibrium expression real quickly, we have Kc equals the concentration of CH3OH over the concentration of CO and H2O squared. Nope, H2, sorry. If we know the Kc value is 0.500, we are looking for the concentration of CH3OH. And we know CO has 0.200 concentration, H2 has 0.1155 squared. We are solving for CH3OH. So you want to go through and isolate CH3OH. So we want to take our 0.55 times 0.200 times 0.155 squared, and you get 0.00240 moles per decimeter cubed, or we can change that to 2.40 times 10 to the negative 3 moles per decimeter cubed. And this number is less than 1, and therefore reactants are being favored. All right, so working an example of this complex one. If we have the reaction SO3 reacts with NO, and you get NO2 and SO2. What we want to put in first, so we're going to go through. So we have this reaction, and the Kc value was found to be 6.78 at a specified temperature if the initial concentrations of NO and SO3 were both 0.03. What would be the equilibrium concentration of each component? So let's set up our table. We need our initial concentrations put in first. So both SO3 and NO are 0.03 as we start the reaction. Remember, products do not exist at the initial point, therefore they have a value of 0.00. Now, that's all the information that's been given to us, so we're going to set everything equal to each other algebraically. Therefore, when we look at the change in concentration, for each of our reactants, we're losing the concentration X. It's a 1-to-1 ratio, therefore we need no coefficient. We are gaining products by the same value of X because it is a 1-to-1 ratio of reactants to products. Then, if we want to go through and look at the equilibrium concentration, we go through and do this mathematically. So we have 0.03.
All right, so you go through and now you need to add up what your equilibrium concentrations would be. So you'd have 0.03 minus x, 0.03 minus x, and then on the product sides, just plus x for each of them since it's a 1-to-1 ratio. Now that we have that information, we could set up our equilibrium expression. So I'm just going to move this up to give us some room. So our equilibrium expression is Kc equals the concentration of SO2 times the concentration of NO2 over the concentration of SO3 times the concentration of NO. Now that we have all that written down, we can go through and plug in the information which we know. Kc's value is 6.78, and then SO2 and NO2 are both X, and when you have X times X over our products, which is 0.03 minus X, and then 0.03 minus X, those can then become squared. So we have X squared over 0.03 minus X squared. We can then take the square root of that answer and the square root of 6.78. When that occurs, we get 2.60 equals X over 0.03 minus X. Then we just solve this algebraically. I'm going to multiply 2.60 by 0.03 minus X so that we can isolate X on the other side of the equation. So when we do that, you get 0.078 minus 2.60x equals x. I'm going to move x over, so we have 0.078 equals, I'm adding our x, so we get 3.60x. Divide by 3.60, and you get 0.022. And that gives us the value for x. Now we can go back and determine how that value gives us the equilibrium concentrations. So therefore, we have 0.03 minus 0.022 for our reactants, and from there we get 0.008 for both of the concentrations of our reactants, and that's in moles per decimeter cubed. And for our products, it's just x, therefore it's just 0.022. With the same unit of moles per decimeter cubed.
The fourth calculation is calculating the concentration of equilibrium from a very small Kc value. So remember, when Kc is less than 1, reactants are favored. So we know the change in the concentration of reactant has to be very little, and it's close to 0. Therefore, we say the concentration of your initial reactant is close to or the same as the concentration of your equilibrium reactant. So we solved this the same as we did in number 3, algebraically using x. And then we assume that the change in concentration is the concentration of your equilibrium reactant equals the concentration of your initial reactant. So going through the example first, the reaction which we're working with is 2H2O provides 2H2 plus O2 gas. So the thermal decomposition of water has a very small value of Kc. At 1000 degrees Celsius, the Kc equals 7.3 times 10 to the negative 18th. A reaction is set up at this temperature with the initial water concentration of 0.10 deciliters cubed. Therefore, we need to set up our information. So the initial concentration is 0.10, 0.00 because they are products. Then we're looking at the change in concentration and then eventually the equilibrium concentration. So we set x as our change. Because we have two waters, it becomes minus 2x. Then we get plus 2x because there's two hydrogens, plus an x for one oxygen. Set this equal to the concentration at equilibrium. So we have 0.10 minus 2x, 0.00 plus 2x, 0.00 plus x. We are making the assumption that the equilibrium concentration equals the initial concentration. Therefore, the equilibrium concentration of water is 0.10. Let's set up our equilibrium expression. Kc equals H2 squared times O2 over H2O squared. If we know Kc has 1.78 times 10 to the negative 3, we're going to set that equal to 2x squared times x over 0.10 squared. Now we just need to solve for x. So if we move that up so we can see it. All right, so we have sorry, that number is wrong. It's 7.3, I apologize, times 10 to the negative 3. All right, so we have 7.3 times 10 to the negative 18th, and I apologize for that wrong number above. And we set that equal to 2x squared times x, so that actually gives us 4x squared times x, which gives us 4x cubed. And when we take the square of 0.10, you get 0.10. So now we have 7.3 times 10 to the negative 18th times 0.10 equals 4x cubed. Go through and solve for x. So multiply the numbers, multiply by 4, take the cubed root in your calculator, and you get x equals 2.632 times 10 to the negative 7th. So this is so we want to look for the equilibrium concentration of your products then, H2 and O2. Well, O2 is a 1-to-1 ratio. So O2 is this value right here. H2 is 2 times x. Therefore, we want to take this value and multiply it by 2, and we get 5.3 times 10 to the negative 7th moles per decimeter cubed for our H2 concentration at equilibrium, because this as stands is O2. because it's just X. All right, the last thing we can look at is how can we manipulate Kc. So Kc, manipulating Kc, depending on what we do, the different questions can ask. They said, well, what if you reverse the reaction? Because Kc is telling us in the forward direction. Well, if we reverse it, then we take the inverse of your Kc value. So 1 over Kc, or Kc to the negative 1. What if you double the reaction coefficients in place of what the Kc value was originally calculated for? If you double the reaction coefficients, you're going to have a squared effect. Therefore, you're going to see Kc squared. What if you take the reaction coefficients and take them by half? Well, if you half the coefficients, that means your Kc value, you need to take the square root of it in order to compensate for decreasing the reactants by half. What if we have two reactions and we're going to add them together? Well, you have the Kc value for reaction 1, you have the Kc value for reaction 2, so we multiply them together to see what the overall effect is. So if we have an equilibrium reaction, and so the equilibrium reaction for, we have 2 Hi, and you get H2 plus I2. So the equilibrium constant for this reaction is 0.04 at a certain temperature. What would be the value of the equilibrium constant for the following reaction at the same temperature? So now we're going to have 1/2 H2 plus 1/2 I2 gives us Hi. So two things have happened. We have an inverse reaction and we have a half reaction. So two things are going to need to happen. We have the reverse, so that means we need to take the Kc inverse, and we halved everything, which means we need to take the square root of Kc. Therefore, if we have our value of Kc, essentially what we're doing is taking the square root of Kc to the inverse value, which means we have the square root of 1 over 0.04, or 0.04 to the negative 1. Take the square root of that value and you get 5.0. So the Kc for this reaction is 5.0 because we reversed it. Our reactant became our product, our products became our reactants, and we halved the coefficients. So we did two things at once. Only knowing the Kc, knowing the two reactions, we could figure out the new Kc value.